Thanks. Right, so today I'm going to talk about unipotent characters and their classification. So like I said yesterday, the unipotent characters, there are two characters. What unipotent classes are two classes of the reductive group. So let me write it this way. So you have on one side the irreducible characters, or irreducible representation of the finite group of Lie type over the complex numbers. We've seen that there was a decomposition which was the analog of the Jordan decomposition for classes in the reductive group. So here I have the conjugacy, and now I can write stable conjugacy classes of, so not the group G itself, but it's Langlands dual. And the Jordan decomposition tells you that if you understand all the semi-simple classes and their centralizers, then in order to understand all the conjugacy classes, you only need to focus on the unipotent classes of the various centralizers. So here inside you have also F-stable, unipotent classes, which we've seen for so yesterday for GLN, that were just given by partitions of n, and like representatives being given by the Jordan canonical form. Okay, and here what will be the analog of the characters which correspond to the unipotent classes will be the unipotent characters. Okay, so I will not define them because that will take too much time and it won't be really enlightening for this talk. But let me just say that, like, some of the properties, and I'll give examples very soon. So first of all, they do not depend on Q. Okay, so but really just on the skeleton of the reductive group. So Steve yesterday mentioned the root system, and so here basically they will only depend on the root system. They've been classified. I'm going to show you the part of the classification. The root system together with the Frobenius. There is still this extra data that comes from the FQ structure. And also, like the unipotent classes, they do not depend on the center. Of the reductive group. Okay, so if I was looking at characters of PGLN or GLN, unipotent characters, they would be the same, but also on the we call it the cocenter, just G over its derived subgroup. Okay, so they're insensitive to like changing the center and the cocenter. So really, they really depend on the type of the group. Okay, so what else do I want to say? Yes, so let me just, so yesterday when I started with the conjugacy classes, I gave various data corresponding to the classes. And here, let me just recall them for the unipotent class. This is what I will need for the classification. So let's just, for unipotent classes. So we have these component groups of the centralizers, which I denoted by AG of U. So there we already seen that they were important when you wanted to understand the rational classes from the geometric classes, the classes for the finite group, from the classes of the algebraic group. But they will also be important for the classification of unipotent characters. And the second ingredient was the order on the classes. So the order on classes, which was given by the closure relation. So if you look only at unipotent elements, if you start with a connected reductive group, the variety of unipotent elements, or the space of unipotent elements is connected. there are only finitely many classes, so you'll have one class which is open and dense, which is called the regular class. So I will denote it by oreg, which is the biggest. Okay? So for GLN, it just corresponds to one Jordan block. Okay? So it satisfies that if you take the closure, this is just all the unipotent elements. And the other extreme, at the other end, you have the trivial class, which is just the class of the trivial element. And in between, you have like various classes. But what I just want to emphasize that for all the simple groups, we know exactly what the classes are and what the order is. So for classical groups like GLN, we have the dominance order on partitions. There are similar things for other classical groups. And for the exceptional, like all the classes that have been sorted out, even in bad characteristics. So maybe, yes, before I forget, I will assume now that the characteristic of the algebraic group, so the characteristic of FQ, is good. Okay, so if I talk about unipotent classes of algebraic group in characteristic P, well, the unipotent classes, they do not vary so much, do not depend so much on the characteristic, except when the characteristic is bad. Okay, so yesterday I showed the example of SP4, but I had to assume that the prime number was odd, which I forgot to mention. So we'll focus on this case, and then, like in that case, everything works as if you were working in characteristic 0, describing the classes and the closure relation. Okay. So I said that I will not construct the unipotent characters, but I can still give a construction of part of them, which are called the principal series representations, or principal series characters. So I'm going to start with this. And this will be enough for GLN, but only for GLN, and not for the other groups, as we will see on examples. So this is really important. So let me just write it. That the unipotent characters, they don't have an algebraic construction in general. So this is, I think, very frustrating when you first encounter this this theory, because you would like, especially when you give a talk on unipotent characters, you would like to have like an easy definition, just by doing some algebra, some induction on the group. But you cannot expect to have it, because the essence, the very essence of the unipotent characters is this the linguistic construction. So they come from the Aladic cohomology of the linguistic varieties. Okay, so here I have my set of unipotent characters. But even though I cannot construct them all with algebra, I still have a small set, which sometimes like covers almost like the set of unipotent characters, which are called the principal series. And these ones, they will have an algebraic construction. Okay, so how does that work? I will choose a Borel subgroup of G. Okay, so if I was working with GLN, I could just take the upper triangular matrices. A maximal torus of G, which is contained in B. Okay, so here in GLN, I could take just the diagonal matrices, the non-singular diagonal matrices. Okay. And so the definition of, yes? And that's the important, I mean, the key thing is that you can always choose B and T such that they are F-stable. Okay, in which case you have the corresponding finite groups. Which are given by just the fixed point under the Frobenius, so the FQ points of T, and the same for B. Okay, so there is, like on these pairs, the group, the algebraic group acts, and by the theorem that we saw yesterday, that comes from the Langlands theorem, there will always be a F fixed point on an F-stable orbit. So you can always, up to conjugation, you can always find a pair satisfying this. Okay. So with this data, I can define what a principal series unipotent character is. So sometimes I will just forget about the unipotent property, but rho is, so I start with an irreducible character of GF. Maybe I should have seen this differently. Well, let's say is a constituent, an irreducible constituent of, if I look at the representation, which is the induced representation from the Borel to the group G of the trivial representation of the Borel. Okay, so I start with the Borel, which is defined over FQ. The finite Borel, I'll take the trivial representation, I induce it up to the group G. It gives me something quite small, actually, that do not depend so much on Q, again, or at least as far as the number of constituents is concerned, irreducible constituent. And all the irreducible constituents are, by definition, the principal series characters. Okay. So if you prefer, so this is just the character of the permutation module G over B. Okay, so maybe a quick example. The smallest non-trivial example is the example of GL2. And the standard for Venus, so G FQ are going to be GL2 of FQ. So B is just a set of 2 by 2 upper triangular matrices, invertible. T 2 by 2 diagonal matrices. Okay, and if you look at G over B as a topological space or as a variety, that's just P1, projective plane. Okay, so if I'm looking at things over FQ, I'm just considering the FQ points of P1. So you have Q plus 1 elements. So I have a permutation module over a set of Q plus 1 elements. So the dimension is Q plus 1. So when you have a permutation module, you can always look at the span of a vector, which is the sum of the elements. This is invariant under the group, so you always have the trivial representation inside. So C P1 of FQ. You always have the trivial representation, C. And here you will have another dimension, representation of dimension Q plus 1 minus 1, so dimension Q, which here turns out to be irreducible. So let's call it V. And this one is an irreducible representation of dimension Q. Okay, and the character of V is the Steinberg character. And by definition, character of V is so denoted by ST, the Steinberg character. So V is just a Steinberg representation of GL2. All right, so that's in this very elementary example. I can do more generally. If I want to understand what happens, I need to understand what this permutation module is. Okay. So for this, I will introduce the Weil group, which Steve defined yesterday. So it's just the normalizer of the torus, the algebraic torus over the torus. It also have an action of F, because F acts on G and T. And I can, I have the a version of the Breuer decomposition for the fixed point of W under F. So the Breuer decomposition tells me how to decompose the permutation module. Sorry, the set G over B. And in particular, this implies that the number of points on the set is just the sum over all the elements in the Weil group, or at least the fixed point under F, of Q to the power of the length of W, the length as an element of this Coxeter group. Okay? And here you have two distinguished elements, the trivial element and the longest element. So you can write it like this: 1 plus Q, the length of W0, plus the rest. Okay? And the counterpart is that if you look at the permutation module, you will have this one will correspond to the trivial representation, or the trivial character, and this one to the Steinberg character. So which means in the principal series unipotent characters, you always have the trivial character, which is the one of smallest dimension, dimension 1. All the other ones will be nonlinear. And you have one of highest dimension, which is the Steinberg of dimension Q to the length of W0. Okay, so here was just 1 and Q. You have nothing in between. But you can have, like, you will have several other principal series characters occurring. Okay. And you can actually tell what they are, all the constituents. So I have a module that I want to decompose. So for this, I should look at its endomorphism algebra and trying to study its representation theory. And here it becomes quite simple, and it's related to the Weil group again. Position is that the endomorphism algebra of this module this is isomorphic to the group algebra of this finite Weil group. Okay. So the consequence is that the irreducible character, the irreducible constituent of this module, which are the principal series character, they're parametrized by the irreducible representation of this Weil group, the complex irreducible representation of this Coxeter group. Sorry, what did I? Sin CG, yes. Thanks. GRFQ. Thank you. Okay, but that's actually, if you, I mean, this is not the natural isomorphism that comes up. I mean, if you change this isomorphism, you will change this correspondence, which is pretty bad for what we want. We want something quite natural or canonical, not depending on any choice. But there there is actually a better isomorphism. If you're really interested in the structure of this algebra, you will have operators. So here I have a basis given by elements of this Cox-Star group. And here for every element of the Cox-Star group, you have actually well-defined operator, which is not something that squares to, which is not something of finite order. So for example, if you take an evolution here, it will not square to 1. So it's a Q, actually a Q deformation of the group algebra of the Vi group. So have a better isomorphism with a Q deformation of the group algebra, okay, which here will be the Hecker algebra with some parameters of this Cox-Star group. Okay, so I don't want to give too many details, but the consequence of having natural isomorphism like this, or this algebra having a natural structure of a Hecker algebra, tells you that you can not only parameterize the representation, but you can also compute the dimensions. So the degrees or the dimension of the irreducible the principal series representations. And there will be Q deformations of the dimension or the degrees of the representation of the Cox-Star group. So here, starting from a character chi, I associate a unipotent character or principal series character rho chi. Then, so this is a character. I can evaluate it at 1. This is the dimension of the representation or the degree of the character. This is a polynomial in Q. And if I evaluate at Q equals 1, then I get the degree of the representation, the degree of the character of the Cox-Star group. Okay. So maybe two examples. This is the Steinberg and the trivial. So inside the irreducible representation of a Cox-Star group, you have two which exist no matter what finite Cox-Star group you're looking at. One is the trivial representation. So if I start with the trivial representation of WF, well, I get the trivial representation of my finite group G of FQ. So the trivial, like I said, it's always a principal series representation and unipotent. And if I look at the sign representation, then I get the Steinberg. So by definition, if you prefer, if you want, representation. So this one has dimension 1, obviously, and this one has dimension Q to the length of the value 0. And you can see that if you evaluate Q at 1, well, you get the dimension of the sign, which is 1. Okay. And yes, and so I said that this gives part of the unipotent representation, but actually all of them in GLN. So that's the theorem that I want to state, is that all unipotent characters or representations of GLN of FQ. So here I could replace GLN of FQ by SLN of FQ or PGLN of FQ. I said that it did not depend on the center or the derived subgroup. So our principal series characters. So this is where type A is really different from the other types, is that you don't really need this the linguistic theory to construct the unipotent characters. You start, it's a very elementary construction. You start with the trivial representation of the Bruel. You induce it up to the group, and then you decompose, and all the irreducible constituents are the unipotent characters. You can compute their dimensions. So the problem of understanding the unipotent characters here is pretty much done for GLN. Computing the values is, of course, much more difficult. So I think Jay will explain like how you can actually, like on this induced model, by inducing not from Borel subgroups but from parabolic subgroups, you can actually single out like the characters, the unipotent characters for GLN. So yes, so that he'll explain this in his talk, I think, this afternoon. Okay, so I'm halfway through my talk, so it's time for a commercial break. So I need the video projector, please. Okay, so that was yesterday's slides, so let me just go through them quickly. So that's the semi-simple unipotent classes that we saw yesterday. Okay, so this is the commercial. So for the young people in the audience, there's going to be a summer school in September in Castro Urdiales. That's in the north of Spain. Very nice area, as you can see. So it's in September. And for a week, and the summer school has 2 parts during the week. The first 2-3 days will be, as it's written, some introductory lectures on finite groups and their representation theory and their modular representation theory. So from maybe the module point of view, probably something that Marcus is going to talk about later today, but also from the character point of view, like Brouwer characters, for example. Followed by 3 days of advanced lectures given by Michel Brouet, Ian Gordon, and Rada. And the concept is that each speaker gives a series of lectures during one day, so 3 to 4 lectures, and each lecture is followed by a problem session of 30 or 45 minutes. Okay, so if you want, it's important to register very, very fast if you're interested in that school. So unfortunately, we cannot offer reimbursement of travel expenses, but we can pay for accommodation for the whole week up to maybe 30 participants. So if you're interested and if you want to learn about these things, then you should get in touch with me or Mandy, who is also a co-organizer of this school. Okay, so that's it for this break. So yeah, so I said for GLN, where is it? Theorem. So all the unipotent characters, there are principal series characters. But I said that the principal series characters, they were parametrized by the irreducible representation of the Weil group. So here I have a complete labeling of the unipotent characters, starting from the Weil group, which is a symmetric group. And the Frobenius acts as the identity on that group. So the fixed points are just the symmetric group. So I get from this proposition that the principal series characters are parametrized by the irreducible representation of the symmetric group, which in turn are parametrized by partitions of n. Okay, so I get a labeling of the unipotent characters, in that case, by partitions of n. And still the same example is that I get the Steinberg and the trivial representation or character as special cases. So for the partition n or the partition 1 to the n. So this is easy for GLN. What happens when you move out from the GLN world? Let's do SP4. So I have to use the irreducible representation of the Weil group of SP4. Again, F acts trivially in that case. So I have 5 irreducible characters, the trivial, the sign, dimension 1. I have 2 other representations of dimension 1, which are exchanged by tensoring with the sign, and the reflection representation of dimension 2, so Chi2. So I get 5 corresponding principal series representation of SP4. So I've tried to keep the same notation. And I said that you can compute the dimension, and you can check if I haven't made any mistake, that if you put Q equals 1 in the last column, you'll get 1, 1, 1, and 2. Okay. So something happens already here, as you can see. So for GLN, you also have formulas for the dimension of the representation, which is really a polynomial of Q with integral coefficients. Here you have fractions which are involved for some of the characters. This is something already which changes from which is specific to non-GLN. Okay, but that's not it. I said that it's only for GLN that you get all the unipotent characters as principal series characters. And you have an extra one, which is called theta 10. So it's not my notation. So it was part of Bama Srinivasan classification of characters. So she had like various labelings of characters. And the one which is unipotent in the theory of Denis and Lusztig and not in the principal series is this theta 10. Okay, and you can recognize it here. That's not principal series. If you put Q equals 1 in the degree, you get 0. Okay, so that cannot be that cannot come from a zero-dimensional representation of the Lie group somehow. So you need more involved tools to explain its existence here. Okay, so that's it for the unipotent characters. So could you turn off the beamer, please? Thanks. All right, but so I haven't said anything about the unipotent classes yet. That was the goal, was to say how the classification of unipotent characters was, or parallel the ones of unipotent classes. So I need to say something about this using this data of unipotent classes. So the first thing you can notice is that for GLN again, we have like the unipotent characters are parameterized by partitions of n, and so are the unipotent classes. So there is an obvious map. So that's the 2 and 2 with the notion of unipotent supports. So for GLN, you have the unipotent characters of GLN of FQ. I just say that they were parameterized by partitions of n. Which are in turn labeling the unipotent classes of GLN. Okay, so you get an obvious correspondence between the unipotent classes of GLN and the unipotent characters of GLN. Okay, for example, so again, the trivial character correspond to the class, so now the regular class, which is the one corresponding to the partition n, and the Steinberg character correspond to the trivial class. Okay, this is a little bit surprising when you look at this parameterization. Like the trivial representation does not correspond to the trivial class, but I will explain this in a minute. What this is this convention that we have to take. Okay, so the question is how, if I want to do this for other groups, there is no, in general, there is no way. So I have I already have only the principal series characters. They are parameterized by the representation of the Weil group. How do I go from the Weil group to the unipotent classes? It's not clear unless you know a bit more about Sprenger theory, for example. But here, I'm going to try to recover that bijection just by looking at the character values now. I could recall that I was interested in the labeling of the characters, the dimensions, but also the character values. Okay. So here, the question is how do you get a better correspondence? It's via the following theorem. So if you start with lambda and mu, two partitions of n, so I can consider the unipotent character or the principal series character corresponding to lambda, and I can look at its value on the class corresponding to mu. So I have to take the points over FQ, and I can look at when it's non-zero. So if it doesn't vanish on that class, then this implies that mu is dominated by lambda, which means that O mu is smaller than O lambda. Okay, and if I look at the value at the class corresponding to the same partition, I really get a non-zero value, and it's some power of q. Q to the some power, let's call it, so I call it d lambda, where d lambda, you can write it explicitly in terms of the partition, but here I would just use the dimension of the orbit. So a half of the dimension of the orbit corresponding to lambda. So, okay, so that's for GLN. So starting from if I didn't know about the correspondence, I start with the unipotent character, and I can look at the biggest class on which it does not vanish, and this is the class corresponding to the same labeling. Okay, and I will do it. I will do the same for the other groups, and that will give me a map which will not be a correspondence, but which will allow me to associate a unipotent class to any unipotent character, and that's the notion of the unipotent support. So the definition. So I start with a unipotent character. So I haven't said what it was, but I've given you the example of SP4. So starting for a unipotent character, I will call a unipotent support is a conjugacy class, a unipotent class. It's an F stable, sorry. Unipotent class O of G, the algebraic group, that's important, such that first of all, you want rho not to vanish on the rational points of, you want rho not to vanish on this class. So this class is geometric. For GLN, a geometric class gives only one rational class, but for other groups, you can have several of them. So I'm just going to consider the average of the value. So such that the sum over all the elements in the orbit of the value of rho at these elements is non-zero. So I look at a class on which rho will not vanish, but also on the average of rho will not vanish. And I will take O to be minimal, maximal for that property. Okay. And so the definition makes sense, but I said that it was a unipotent support, but it was shown by Lusztig and by Geck that the unipotent support is actually unique if you work in good characteristic, and then also in bad characteristic by Geck and Mahler. But I would not use that fact. So it's a theorem of Lusztig and Geck is that the unipotent support is unique. And we will denote it by O of rho for unipotent character rho. Okay, so for GLN, this theorem tells you that the unipotent support of rho, so if G is GLN, the unipotent support of rho lambda is just the class O lambda. Okay, that's what it says, and it gives a one-to-one correspondence for GLN. Here, for other groups, the situation might be a little bit different. You can group together the unipotent characters with respect to their support. So you get for general G a partition of the set of unipotent characters with respect to the support. So let me denote it by UCH of O, where O is a unipotent class, F-stable unipotent class of G. Okay. So for GLN, for every class, this is just a single unipotent character. But for other groups, this will be different in general. So there are two things that can happen. This could be empty, or this could contain more than one element. And we'll see on the example of SP4 that it can be the case. Just a remark. UCH of O can be empty. And it can also happen that the number is bigger than 1. And for like the more complicated your group is, and the further from the type A you are, and the more frequent these two phenomena will occur. Okay, so if
is that the only F stable, right?
Yes, I should say F stable. Thank you. So if you if you're in the situation where it's non-empty, the class is said to be special. Okay, so in particular, all the classes of GLN are special, but for other types, that won't be the case. So let me give you the example of SP4 again. We need the projector. Sorry. Okay, so these were the characters, the unipotent characters of SP4. Okay, so this again for when the characteristic is good, these were the unipotent classes of SP4. So out of these 4 classes, there is, so let's remove the dimension. We don't care about this right now. So out of these 4 classes, there is one which is not special. So let's get rid of it. Okay. And then, yes, maybe I should have written something else before. Okay, let me just continue on before showing the example. Let me just continue on the classification, sorry. I said that, so something I haven't used, so I've used the order on the unipotent classes, but I haven't used the component group yet, or at least in the hidden way to know the conjugacy class for the final group. But here, for the classification, it would be important. Of the unipotent characters in a special class. Okay, so you start with O being F stable and special. So you have an element U. You can take any element which is stable by F in U. So the class is special, so it contains a rational element. And I can consider this group AG of U, which is the component group of the centralizer. And this is the group that will help me to parameterize this set. So I said that the unipotent characters, they do not depend on the center of the group. Here, this component does. You have the image of the center can be non-trivial in that group, so it can make it bigger. In general, if you start with a simply connected group, for example, this AG of U will be bigger than the one for the adjoint group. So for SLN, if you take the regular element, that's the whole center of SLN, whereas for PGLN, for regular element, that's trivial. Okay. So if I want something which is independent from the center, I need to consider, I need to mod out by the center. But actually, I need to do a little bit more, which is what Lusztig did. So he defined some quotient of this group, or this finite group, which he called canonical. Which, like, it has a general definition, but he could determine them all. So it involves like the Springer theory. But there is an intrinsic definition of this A of O, A sub O, sorry, which do not depend on the center now. Okay, so which is really the same for PGLN, GLN, and SLN. It would be 1 for other groups. I'll just give the example. So here, I said that, yes. So AG of U, I say I want at least to get rid of the center, but I have to get rid of more in general, but not for SP4. So here, the regular class that had a non-trivial AG of U, well, this A sub O, this canonical quotient, becomes trivial, whereas the class 2 square, there is an actual Z over 2 which doesn't change. Okay, so what, for SP4, what are the unipotent characters corresponding to O? So this is the unipotent supports. So for the regular, it's always the trivial representation. For the trivial class, it's always the Steinberg representation, or Steinberg character. And here, you don't have any choice. I mean, you have only one class left, one special class left, and you have 4 unipotent characters left. So this forms like the whole unipotent characters corresponding to the class 2 to the square. Okay. But if you don't know a priori about the number of unipotent characters, how can you guess, or how can you recover the fact that you have 4 of them? You have a Z over 2. So how you get 4 from Z over 2? By doubling Z over 2. So this is, okay, this is a very small example. So it could be, it's not very convincing, but this is really like how the classification started, from example like G2, where the component group will be actually S3, for example, so a little bit bigger. But how, I mean, how, once you have determined the number of unipotent characters, how can you tell the number of them, yes, using just like this small finite group, Z over 2, and how can you parameterize them and then try to compute their values? So that's what I want to explain for the remaining 10 minutes. So when I say doubling, it's really, I mean, there is something deep behind doubling a finite group here. When you have a finite group, you can consider the Driefold double, and it's representation theory, and this is the object that should occur here. So I will not explain in detail, but let me just give the parametrization explicitly. So it's a theorem of Lusztig. So there is a bijection between the set of unipotent characters with unipotent support O, and so I say to double, but there is 2 ways to double. You can just put 2 copies of the group, or you can look at the group and its representations. Okay, so this is how you should do it. So I look at pairs A and psi, such that A is an element of this canonical quotient, and psi is not a representation of the whole group, but of the centralizer of A. So an irreducible character of the centralizer of A. And this has to be taken up to conjugation by A. So A acts on the pair by simultaneous conjugation, and you look at the conjugacy classes. So to a pair A psi, I get a unipotent character, rho sub A psi. Okay. So here, I don't remember if I did here, maybe not. Sorry, not really. Okay. So yeah. So in particular, if you start with something which is connected, if the centralizer of U being an element of O is connected, then here you get only one element because you have a trivial group, and so you see H of O contains only one unipotent character. So there is only one unipotent characters of unipotent support O, and this is what happens for the trivial class, whose centralizer is the whole group, which is a connected group, and for the regular class, whose centralizer is the center of the group, but since I modified by the center, I get nothing. Okay, so let me finish by explaining some insight for this classification, where does it come from? You can see it on the values of the unipotent characters. So if I look at the values for these characters, so I know, so because of the definition of the unipotent support, I know that they vanish on the regular class. Their unipotent support is the class which is just below. So they have to vanish on things which are bigger. So I can remove this. On the trivial class, this is just the dimension of the unipotent characters, which I've copied here. So the last one being the cuspidal one. Okay, I can look at the class which was just below the regular class, so the sub-regular. So for since the component group is Z/2, I get two classes which are geometrically conjugate, so under the algebraic group, but not rationally conjugate. So the characters might have different values on this class, and they do have different values, as you can see, but the values are still simple. If I looked at the last unipotent class that I haven't looked at, so this 2, 1 square, I get these values, and again I have fractions occurring in here, which is particular to things outside of GLN. But I can look at other values on mixed classes. So from the first lecture, remember I had this involution S, whose centralizer was not a Levy subgroup, and it turns out that it's the unipotent element corresponding to the class 2 square can be taken to centralize this S. So I have a mixed class, and the values on this class are much more difficult. Okay, so from the classification here, if you look just at the character table, or the part of the character table is complicated, and you can't see really what the classification, how the classification helps to compute the values. Okay. So how you can solve this problem? So the values, like I said, are complicated, but it was already observed by Bama when she was computing the character table, is that if you, instead of looking at classes, you do some small combination of classes, or you do some small combination of characters, things vanish a lot more, and the values become much nicer. You get rid of the fractions. You have, most of the time, you have only monomials. And it's what you have to do to simplify the characters. Somehow the algebraic objects, the characters, they have complicated values, but you can change them a little bit so that they will come from geometric objects, which will have simpler values on the classes. Okay, so let's, so I fix again O special class. And I consider A in AO and psi in the centralizer, an irreducible representation of the centralizer of A. And I will define a transform, which we now refer to as the non-abelian Fourier transform. So F corresponding to A psi will be, so it's a big sum, so it's complicated. So I want to look at all the other pairs like this, B phi, and I would like to do, if I want to do some kind of Fourier transform, I would like to apply psi to B and phi to A, can conjugate, and then that would be the coefficient of this row B phi. And I can only do this if it makes sense to look at the value of phi at A and psi at B. So if B centralizes A, because psi is an irreducible character of the centralizer of A. Okay, so for this formula to make sense, I have to make it more complicated, and I have to look at all the conjugates of A which centralizes B. And now I can look at this formula here that I have to normalize. So it's complicated. It gets simpler when you have an abelian group, but everything, I mean, you can do all the computation. It's a small finite group, this A of O, so you can do this transform. It's really not hard to do it. So let's do it on SP4. So I have a Z/2 for this big family. So instead of looking at the characters of Z/2, I will look at elements here. It's easier. So pairs have 4 elements. And let's to ease the notation, let's change it to plus or minus. So plus is a trivial element and minus the non-trivial element. Okay, so under Lusztig's parameterization, I get plus plus is the row 2. So the first three are the principal series. And the row 10 was the theta 10. I changed the notation, sorry. If I use this formula, what do I get for the Fourier transform? I get this small sums, which look complicated. But if I look at the values now, so that's the values of the unipotent characters. If I look at the values on the classes, I get things which are much easier to handle. This is F1, this is F1 prime, this is F2, and this is F10. Okay. So that was already observed by Bama when she was computing the character table. Okay. So how can you recover some of the values using the classification? This is what the point of this lecture is, to compute the values. So if you know this transform, you just need to understand what the values of these Fourier transforms are. Okay, so let's focus on this 4 classes. So the unipotent that splits in 2 rational unipotents, and the mixed class. So you can see some similarities. If I look at the parametrization in terms of the Drinfeld double, so here the plus and minus, you can see that the first component of the pair of plus and minuses tells you about on which class you do not vanish. Okay, the plus will be the unipotent class, and if you have a minus, it's the non-unipotent one. Okay, and then for the second component, if I have a plus, it means I have plus q, or plus 1 and plus 1. You don't really care about the power of q. What's important is that you get, if you look at the sign, that's the trivial representation. Okay, and the minus, that's the sign representation. And Lusztig's theorem tells you that this is something more general, that starting from a pair like this correspond to a local system on some mixed class, and you can recover the value on that class by just taking the characteristic function of this local system. So this is something very, very deep and helpful to compute the values. And I'll stop here. Thanks. I don't know. So the usual thing to do is more is to try to evaluate at other roots of unity than 1. So if you put q equals -1, for example, you'll get some characters will have non-zero values, and that will correspond to the dimension of some other complex reflection group in general. So there is a whole theory. So here in SP4, I'm not sure you can see it. But if q is either a -1 or a primitive 4-foot of 1, the various dimensions that you will get make sense as dimensions of some complex reflection group. So here would just be the dihedral group for +1 or -1, or the cyclic group of order 4 if you replace by I or -I. But that's not exactly what you're asking. But